So let's take a look at an example. Suppose an investor wants to compare the risks associated with two different stocks. Risk could be defined and measured in a few ways, but let's say we're going to measure risk as the variability in the stock's daily price changes. We said that variability was usually a bad thing, as a process or system that exhibits variability usually has behavior that's more difficult to predict. However, there are some financial engineers who try to exploit variability by buying low and selling high, where the difference in low and high can be big when stock prices are highly variable. But let's not get into that. Let's just assume that variability is a bad thing. Let's say we obtain a random sample of 25 daily price changes for stock 1 and a different random sample of 21 price changes for stock 2. Note that these are not the same days, okay? So we're not using a matched sample design. We're assuming independence of these two samples. So with 95% confidence, are the variabilities of these two stocks different from each other? Okay, all we want to know is if they're different from each other. So our hypotheses here would just be, is the variability, the variance of stock price 1, the stock daily change in stock price, is it equal to that of stock 2, or are they different from each other? Okay, just want to know if they're different from each other. Okay, so we collected a sample from stock 1 of 25, and we found that the sample standard deviation in daily stock price change was 0.824. Then we collected a sample from stock 2 of size 21, and we found that the standard deviation was 0.551. Okay, so now we want to answer this set of hypotheses. Okay, so our F statistic, F naught, is S1 squared divided by S2 squared. That is 0.824 squared divided by 0.551 squared, and that number is 2.236. 2.236. Okay? So now let's go to our F distribution, and we'll use the critical value approach. Okay? We wanted to be 95% confident in this result. So let's put 0.025 in the upper tail and 0.025 in the lower tail. Okay? So we need to go find these values on this f-axis with degrees of freedom in the numerator of 24, in 1 minus 1, 24, and in the denominator of 21 minus 1, which is 20. Okay? So we need to go find this value right here. This critical value is F for 24, 20, and 0.025 in the upper tail. Okay? And for down here, we want 0.025 in the lower tail. That would be 1 minus 0.025 in the upper tail. Remember, our F distribution table gives us the upper tail values, or we'll figure this out in a second. But we think about this in terms of upper tail values, okay? The F table gives us only these small upper tail values, but there's a relationship between a lower tail value and an upper tail value, okay? So for here, we want 1 minus 0.025 in the upper tail. That's degrees of freedom numerator 24, denominator 20, and 0.975 in the upper tail, okay? We know the relationship here, printing out tables with 0.025 in the upper tail, 0.975, and all these different combinations would take a lot of paper, but luckily we have a mathematical relationship, and that is that this is equal to 1 over the inverse of the F distribution, an F value, with 0.025 in the upper tail, alpha over 2 in the upper tail, but the degrees of freedom switched. Okay, so this is equal to 1 over F of degrees of freedom numerator of 20, denominator of 24, and 0.025 alpha over 2 in the upper tail. Okay, this we can look up, this we can look up. If we go to the F table, the F table associated with 0.025, go over to column 24 down to row 20, we should get that this value is 2.41. Okay? And if we go over to our F table with 0.025 in the tail, go over to column 20, down to row 24, we should find that this value is 2.33. So 1 over 2.33, if we work that out, that's 0.4292. Okay, so the critical value here, using the critical value approach, 2.41. Critical value here is 0.4292. So now we take our test statistic, 2.236, we plot it where it goes. That's around here somewhere, lies in the non-rejection region. Okay, our test statistic lies in the non-rejection region. We would not reject the null and conclude that the variance in daily stock price change for stock 1 is equal to that of stock 2. Okay? Both of those we could say are equally roughly dispersed, the same. We could say that the variability of daily change in stock price for stock 1 is equal to that of stock 2 with 95% confidence.